All right, so now we're going to take a look at problem 9 from the universal gravitation sheet. This one is kind of cool, I thought. It was looking at the sun and the solar system, but the sun in particular, moving around the center of the Milky Way galaxy. And so you say, well, that's kind of a circular motion sort of thing there, right? And so we're going to treat it like it's a circle. And they give us some values, all right? So they tell us that the sun is near the outer edge of the galactic disk, 30,000 light years from the center. And they tell you that it travels around at a speed of 250 kilometers per second. And so they want to know what's the period, what's the time it takes to go around once. And so you say, okay, we'll go ahead and we'll do, let's see here, a picture, and you'll say, I don't know which way to make this problem. I'm sure it depends whether you're looking at the top or the bottom of the galaxy, right? Okay, but I don't know how many spiral arms there are in our galaxy. Are there 3 arms? Are there 4 arms? I don't even know. I'm going to represent it like this. So we're like out here somewhere, right? Okay, so there's the sun. And they tell us here that this distance out here, that's 30,000 light years, 30,000 LY. And we know that as we travel around, we have this tangential velocity of 250 kilometers per second. I'm going to change that 250,000 meters per second, right? Okay, I'm going to use like normal units for this one. So that 30,000 light years, I'm going to need to convert that to meters, right? And so I just did a Google search, and it says, hey, convert light years to meters. And when you do that, I mean, we could go through the whole dimensional analysis thing if you want with the speed of light. 3.86. No, forget. Let's just do this. So I got 9.46 times 10 to the 15 is basically that conversion factor that I found. Meters equals 1 light year. Okay. So I was able to do the calculation there, multiply this times the conversion factor, and I got that distance, that 30,000 light years, came out to be something big. Okay, sorry, I didn't even bother calculating it out. I just put it into the calculation. So good enough. So basically, what I'm going to do here then, you say they want to know the time it takes to go around. You say, well, if I'm assuming, and I don't see any other way of doing this problem, but if we are assuming that the sun is making a nice circle around the galactic center, then I can go ahead and say the relationship between the speed and the period by just saying, hey, speed is distance over time. So speed is the distance around once divided by the time to go around once. Okay, and so speed is the distance to go around once, the circumference, divided by the time to go around once, the period. Rearranging the period is 2 pi r over v. Put in my values, 2 pi, that distance is 30,000 times 9.46 times 10 to the 15. And then the speed, they told us, was 250,000 meters per second. And so I punched that in my calculator, and it spat out a value 7.133 times 10 to the 15th seconds. Okay. Now, maybe it might be nice. Seconds is not a real. I mean, it's the metric standard unit, right, for time. But it might be nice to get that. What's that in meters, right? So I might do a conversion factor on that. I might do 7.33. Oh, sorry, 7.133 times 10 to the 15, and then I might go ahead and say, okay, well, that's how many seconds. Let's divide that by 60. So now it's minutes. Divided by 60 again. Now it's hours. Divided by 24. Now that's days. And I can divide by, do you like to use 365 days in a year or 365 and a quarter day? Let's just do 365. And I get a value here, 1, 2, 3, 4, 5, 6, of like 2.26 times 10 to the 8 years. Okay, so that's about, well, what is that? 226 million years to go around once. Okay, I'm going to accept that value. Okay, I really feel like I had to double check that one, but we'll say that's it. Okay, so that's part A. Okay, so part A, finding the period of the orbit. Okay, now I do part B. Part B says, okay, now that you've got that, of what order of magnitude is the mass of the Milky Way galaxy? Now, by the way, order of magnitude, what that means is like to what power of 10 is what that means. So you're not asking for like really precise here, which is a good thing. So you say, okay, so what's the order of magnitude is the mass of the Milky Way galaxy? So it says we're going to assume that the sun is zipping around, and basically it's the mass. We're on the outside edge, so we can assume that pretty much the mass of the rest of the galaxy is trying to pull us in towards the center, right? Just like standing on the Earth, you get pulled in toward the center by all the mass of the planet. Same sort of idea. So if I do that, again, what have I got to work with? They gave me like speeds and this, and this is a radius of the circle. You're like, oh, so it's a circular motion problem, right? It's an orbit problem. And so you say, okay, if I'm looking at the sun as my system, I'm going to do sigma F as ma. I'm looking at the only force being that gravitational force toward the center of the galaxy. And that acceleration, this is the radial axis. So that's the centripetal acceleration. That's speed squared over r. Gravitational force, big G, mass of the galactic center, mass of the sun, no, mass of the galaxy, really. Mass of the galaxy. Mass of the sun over that distance out, distance to the center of the galaxy squared. And then this is the mass of the sun. That's the thing that's going in circles, the sun in this problem. And then the speed, we got the speed, right? They gave us that. That's awesome. I don't have to mess with that. That's really nice. Okay. Okay. You'll notice right away that the massive thing going around the circle drops out. Bang, bang. That's awesome. We're trying to find the mass of the galactic center. So I'm going to move that r. I can cancel one of these r's right now. Move this r over there. So I'm going to get that the mass of the galactic center is going to be v squared times r divided by big G. Right? So I can put my values in. That v, that was at 250,000 squared. That distance out, that was at 30,000 light years times 9.46 and 10 to 15 light years, or meters per light year. (30,000 times 9.46 times 10 to 15, right? And then divided by big G, 6.67 times 10 to the negative 11. You're like, this is going to be a huge answer, right? Because look, dividing by 10 to the negative 11, so I got times 10 to the 11, I got a 10 to the 15, square this. It's going to be a huge number. Go figure, the mass of the galaxy is huge, right? And so when I punch this in my calculator, I got this value. I got that the mass of the galaxy came out to be 2.656 times 10 to the 41 kilograms. Now, they said they want the answer, like, what's to the nearest order of magnitude? You say, hey, is this closer to 10 to the 41 or 10 to the 42? This is closer to 10 to the 41. So basically, 10 to the 41 kilograms is the answer they're looking for. All right. And there's one more thing. They say, okay, now look. What's the order of magnitude of the number of stars then in the Milky Way? Assuming that all the stars are about the same, that the sun is an average star, which you hear. I'm not sure how true that is, but we'll go with it. We know the mass of the sun. It's at the top of the page. It's 1.991 times 10 to the 30th kilograms. So I can say how many sun's masses would fit into this. What did I say? 1.991 times 10 to the 31. You want to be really rough with it? Really rough? And say, or 10, 1.991 times 10 to the 30. You can just say, let's just round that off to 10 to the 30. Like, how many 10 to the 30s go into this? You're like, oh, 10 to the 41 divided by the mass of just one star, mass of the sun, is roughly 10 to the 30th, right? And you're like, oh, that'll be 10 to the 11th stars in the Milky Way galaxy. And you say, hey, 10 to the 11th, that's what? 100 billion? 100 billion. So on the order of 100 billion stars. So in the Milky Way galaxy. That's a lot. And that's just one galaxy out of all the many, many, many galaxies out there. billions of galaxies. Yeah. So I mean, it's just mind-boggling how huge the universe is. Just absolutely incredible. And it's even more surprising when you realize people didn't even know about the existence of galaxies, um, until the last couple hundred years, right? Okay, they didn't have telescopes big enough to see those faint objects, to collect enough light to see those very distant objects. They first started seeing, what was it? They started seeing kind of like little blurry bits, right? And this guy Messier, like, kind of cataloged all these, French guy Messier, calculated like all these little blurry spots in the sky, and later on they figured out, oh, those are galaxies we're seeing. Anyway, incredible. Do you know the story about the Hubble Space Telescope and how they did that survey? They pointed the Hubble Space Telescope to like the emptiest spot in the sky they could find, right? And they kept it there, and like they kind of collect light over time, right? And they close it, and they collect light, and they just store light for like a long time, so they could pick up all the faint objects. And when they did that, I don't know if you've seen those Hubble Deep Field photographs. That's what you look up. Google up Hubble Deep Field, and you'll see that was the blackest, emptiest part of the sky they could find, covered in galaxies. It's just incredible how much stuff. But anyway, okay, I got off track there. Okay, but 10, 11 stars, what we got out of this? All right, that was problem 9.